Building on our discussion about scaling, let's dive into one of the most critical performance metrics in system design: latency. As the title suggests, you can think of this simply as the wait time. Technically, latency is the time it takes for a single request to be completed. It's the delay between a user action and the system's response. To visualize this, let's use Professor Alex's favorite analogy, the kitchen. Look at this image here, representing the process. In this scenario, latency is the specific duration from the moment you order your burger to the moment it actually arrives on your table. That individual wait is your latency. In our systems, we usually measure this in milliseconds. Remember, our goal is straightforward. Lower is better. We want that burger and that data to arrive as fast as possible. Now that we understand the wait time for one request, let's see how that differs from the total volume of requests a system can handle. While latency is all about the speed of a single request, throughput is all about the total volume. It's the width of the pipe, so to speak. In terms of system performance, we look at how many requests can be processed within a specific time frame. Usually, we measure this using the standard metric of requests per second, or RPS. It tells us how much load the system can actually sustain. To make this clear, let's go back to our kitchen analogy. If latency was the time it took for one customer to get their burger, throughput is something else entirely. Throughput focuses on the output capacity. It answers the question, how many total burgers can this kitchen produce per hour? You could have a kitchen with 10 chefs working at once. Even if each burger takes 10 minutes to cook, they might be putting out 100 burgers an hour. In system design, our goal is almost always to maximize this volume. Higher throughput means more users served and more data processed simultaneously. Now, let's see how these two concepts, latency and throughput, actually interact with each other. Building on the concepts of speed and capacity we just covered, let's look at how latency and throughput interact. A great way to visualize this is by imagining a toll bridge. Latency is the time delay for just one car to cross that bridge. From the driver's perspective, this is the only metric that matters: how fast can I get to the other side? Throughput, however, is the total number of cars that cross the bridge in an hour. This is the volume of the system. While the driver cares about latency, the bridge operator cares about throughput. This visual helps distinguish between the two. One is about individual speed, the other is about total system volume. Here is the critical takeaway. A system can have low latency, but also low throughput. If you have a single lane bridge that allows a car to zip across in seconds, your latency is great. But if that bridge only fits one car at a time, your throughput is very poor. Keep this trade-off in mind as we prepare to dive into the CAP theorem next. Building on those trade-offs between latency and throughput, we now arrive at one of the most fundamental principles in distributed systems, the CAP theorem. It essentially defines the limits of what we can achieve when data is spread across multiple servers. First, we have consistency, or C. This ensures that every node in our system sees the exact same data at the same time. If you write a piece of data to one node, any subsequent read from any other node must return that updated value. Second is availability, the A. This means that every request to the system receives a response. Even if some individual nodes are down, the system stays up and remains functional for the users. And third is partition tolerance, or P. This is the system's ability to continue operating even when the network connecting the nodes fails or drops messages. In a distributed world, network partitions are an inevitability we must design for. Now, here's the core of the theorem. You can only pick two of these three guarantees at any given time. It's a rule of nature for distributed data. If the network breaks, you must choose between staying consistent or staying available. As we see in the note below, a perfectly consistent and available system simply cannot exist if there's a risk of network partitioning. Let's take a closer look at each of these pillars, starting with a deep dive into consistency. As we just discussed, the C in CAP stands for consistency. It's the fundamental promise that your system won't give conflicting answers about the state of your data. In technical terms, consistency means that every node in the system sees the exact same data at the same time. If you update a record on one server, any subsequent request to any other server must reflect that change instantly. To make this more concrete, let's go back to our restaurant analogy. Imagine the host at the front desk updates the price of the daily special on the digital menu. In a consistent system, the kitchen sees that new price immediately. There's no confusion where the waiter is charging $12 while the chef still thinks it's $10. Everyone is perfectly synchronized. This is absolutely essential for banking and financial transactions. You wouldn't want to withdraw money and then see your old balance when checking from a different mobile app or ATM. Accuracy is the priority here. But there's a catch. If the network is slow, forcing every node to agree before finishing an update might slow things down. Sam, you've been thinking about data in different locations. What kind of problems do you think arise if we insist on perfect consistency when the servers are far apart? Building on our discussion of consistency, the second pillar of the CAP theorem is A for availability. Availability means that every request to the system receives a response. Even if some nodes in your cluster fail or are undergoing maintenance, the system as a whole remains operational and responsive. It prioritizes staying online over having the most up-to-date data. To make this clear, let's look at our restaurant analogy again. Imagine a 24/7 diner. The doors never lock. Even if the head chef calls in sick, the restaurant stays open. You might get a simpler meal, or maybe the soup was made earlier that morning rather than just now, but you aren't met with a closed sign. You get served no matter what. In the digital world, high availability is crucial for platforms where any downtime results in lost revenue or user frustration. Think of social media feeds or news portals. If you refresh your feed and see a post from 10 minutes ago because the very latest one hasn't synced yet, you'll likely keep scrolling. But if the app shows a 404 error and won't load at all, that's a failure in availability. Now, let's see how the final piece, partition tolerance, ties this all together. Now, we reach the PE in CAP, partition tolerance. While consistency and availability are about the state of our data, partition tolerance is about the reality of our infrastructure. The core concept here is resilience. A system is partition tolerant if it continues to function even when the network links between its servers break. In a distributed system, servers are often in different racks or even different countries. We need them to handle silence from their peers gracefully. To visualize this, look at this illustration of a network break. Let's use our restaurant analogy. Imagine the front desk cannot reach the kitchen because the intercom system is broken. If the restaurant has partition tolerance, the host can still take orders, and the chefs can still cook, even if they can't talk to each other right this second. They have a backup plan. Here is the critical takeaway. In the modern global internet, network failures are a fact of life, not an exception. This makes PA a non-negotiable requirement. You can't choose to ignore network partitions. You can only choose how you respond to them. Now that we've defined all three, consistency, availability, and partition tolerance, let's look at why we have to make some very tough choices between them. Building on our definitions, this brings us to the famous pick two rule. In any distributed system, you are essentially choosing which side of this triangle you want to live on, because you simply cannot have all three at once. This triangle visualizes the trade-off perfectly. Since network partitions are a reality we can't avoid in modern systems, we are usually forced to decide whether we lean toward the CP side or the AP side. When we choose CP, or consistency and partition tolerance, we are saying that data accuracy is our absolute priority. We won't settle for close enough. As noted here, the system will actually stop responding or return an error if it can't guarantee that the data is perfectly synced across all nodes. It's safer for things like banking, but it means the system isn't always available. The alternative is the AP approach, focusing on availability and partition tolerance. This is where we prioritize keeping the lights on. In an AP system, the goal is to keep serving requests no matter what. You might get a slightly older version of the data during a network split, but the service stays up and running. Think of a social media like. Count it's okay if it's a few seconds out of date, as long as the app doesn't crash. Before we move to our final takeaways, I want to hear your thoughts on how we decide which one to use. To wrap things up, let's bring everything we've discussed today together. We've covered a lot of ground, from basic definitions to the complex trade-offs we just analyzed. First, always remember that system design is the blueprint of your software. Just like building a house, having a solid foundation and a clear plan is what prevents the whole structure from collapsing later. A core theme throughout our session was the balance between functional requirements, the what, and non-functional requirements, the how. A system that does everything but is too slow to use is just as problematic as a fast system that does nothing. When you're planning for growth, remember Chloe's grocery store analogy from earlier. Horizontal scalability is your best friend. Adding more lanes, or servers, is the modern standard for handling massive scale. And finally, we have the reality of trade-offs. The CAP theorem proves that we can't have it all. As an architect, your job isn't to find a perfect solution, but to make the right choice between consistency and availability based on your users' needs. Great job today, everyone. You now have the fundamental tools to start thinking like a system architect. Keep observing the apps you use every day and imagine the design choices behind them. Thank you for